Good afternoon, guys. So in this session of the course EE222, lecture 6, we're going to be talking about the three-phase AC circuits. But let's first do a quick review of what we have covered so far, so that will refresh our memory. So we started the course by making an introduction about basic mathematical functions and trigonometrics, like especially the sine wave. And when we talk about sine wave, remember we were talking about RMS, peak, frequency of the frequency of that sine wave, and period. Once we know the frequency, we can determine the period. And then we talk about some terms of conversion between polar form, rectangular form. How do we convert from one to another? All of these basic terms and skills are needed to solve any AC circuits, and we use them. We use all of this introduction to solve lecture 2. To start by, we started by a series AC circuits, right? And in that series AC circuits, that's a quick example of series AC circuits. So let's say we have an RLC circuits. So this is your R, this is your XL, this is your XC, and this is your applied voltage, and that's a sine wave, right? ES, let's say, okay? And this ES is typically given either as a sine wave or in polar form. So for example, here let's say this is 100 angle of 0, so this is a polar form volt. And let me just for the sake of the discussion, let me just put a number. Let's say this is 3 ohm, that's 2 ohm, and this is 6 ohm, right? And this is a series AC circuit. Everything here is a single phase. It's only one source with a loop, a series loop. So this is going to be your current. This is the supplied voltage. And remember, before we start doing any solution or analysis to the circuits, make sure that XL and XC are given in ohm. If they're not, for example, if they are given in Henry, millihenry, or farad, microfarad, then you have to convert them to ohms, to impedances. You cannot deal with inductance and capacitance directly. You have to convert them to impedances. Right, that's first one. They're already given here as impedances in ohm, so don't forget. I'm missing something here for you guys to focus on. Don't forget to put the J here and the minus J here for the XC. And then you can start with the analysis. And for the AC, for the series AC circuits, so first we calculate the Z total. It's just summation basically here. And then after Z total, we draw the phasor diagram or the impedance diagram first. Impedance diagram, right? An impedance diagram, right? You have to draw the resistance XL, XC, and the Z total. And once we draw it, then we typically look for the currents. And here we're just using Ohm's law. The currents here is nothing but ES over Z total. And remember, everything here is polar, right? There is an angle and magnitude, as we did before, right? So this is the I current or source current, and since it's series, it's only one current for all of them, right? So that's current, and then after we get the current, we can determine the voltage per every element. So this is gonna be VR, this is gonna be VL, and this one is gonna be VC, right? So I can typically again apply Ohm's law for VR. So VR is basically going to be I times R. VL is going to be I times JXL. That's VL. I times JXL. Don't forget the J. And for the VC, so it's going to be I times minus JXC, right? This is one way. Or another way, since it is series here, we also have to learn how to apply voltage divider rule to find the individual voltages, right? To find these voltages. Once we found these voltages, we need to make sure that our solution is correct. So if you add them up, if you add VR plus VL plus VC, and your solution is correct, you should get here the total ES, because it's KVL basically. And then we are sure that KVL is applied, right? After KVL, we check KVL, we bring all the voltages, then you need to draw what? The phasor diagram. Phasor diagram where you have to draw voltages and currents on x-axis, imaginary axis, as we have been doing the past 6 or 7 weeks. Phasor diagram, and then after that we need to calculate what? The power. And when we talk about the power, at that point, it was only the real power consumed in the resistance here, right? And this is measured in watt, right? And after that, we move to another type of power where we can find the power absorbed by the XL, or saved or stored by the XL and released back in the second half of the cycle. And this was a QL. And for the capacitor, it was a QC, right? And we add them together. Remember, this is a real number. These two are imaginary numbers. So you cannot just add them directly. We have to consider the J here and the minus J here for the QC, as we did before. So this was for series. And also, we can bring the power factor from here. So the power factor here is basically cosine of theta of Z total, or cosine of theta voltage, source voltage, minus theta current, that current, or power over total S, total apparent power, right? This is how we find the power factor. And remember, we always think about lagging or leading from the first look to the circuit. If it is a pure series like this one, we can directly determine whether it is going to be lagging or leading. Basically, we look for the higher impedances among the RLC here between XL and XC. As all XC is higher here, so it's going to be leading power factor. If XL was higher, then it would be lagging power factor, right? So this was about the series circuits. And then after that, we move from the series circuits to parallel circuits. Parallel circuits, and again, let me just put a quick example here of parallel circuits, parallel AC circuits, right? Let's say this is parallel, so I have a source here again, and now this is my resistance, my inductance, my capacitors, and since it's parallel, all the voltages here are nothing but ES, right? And let's say this ES now is given as a sine wave, so ES, let's say it's 141, for example, sine of omega t plus 20, for example. So now the angle of ES is a 20, is not 0 in this example. And this is a sine wave. So first step, you cannot use sine wave directly to do the analysis, the solution of the circuit. You have to convert the sine wave to polar form. In that polar form, we're dealing with the RMS. Remember, since this is sine, this is the peak of the sine. So you want to bring RMS, that's 141, it's the peak over root of 2. And the angle here will be 20. This is going to be your source voltage here, right? So let's say this is R, just for the sake of that solution, I'm just going to put some numbers here. Let's say this is 5 ohm, let's say this is 10 ohm, and let's say this is 20 ohm. And again, don't forget the J and minus J for the XL and XC. So this is basically J, this is basically minus J for the capacitor. And now, as we said, it's parallel, so it's the same voltage in all of them. Now this is going to be your total current, or IS. This is the current here in the resistance. This is the current here in the XL, so I'm going to call it IL. And this is the current here in IC, right? Okay. So what we usually solve in parallel circuits. So this is now number 3, parallel AC circuits. Now, we started by calculating here the total admittance, right? So first go and bring the total admittance, which is opposite to the total impedance, right? So once you bring total admittance, you can bring Z total. Right, what else? After total admittance, you're going to be asked to draw the admittance diagram. So in the admittance diagram, we have to draw the opposite of the resistance, 1 over R, which is conductance, G. The opposite of the XL, 1 over XL, which is susceptance, PL. And the opposite of the XC, which is 1 over JXC, which is BC, susceptance of the capacitance, right? And the total admittance. After that, we know the voltage is the same, and the voltage is given in this question. So we can calculate the current, right? Now the current here, the total current, IS by Ohm's law, right? By Ohm's law it means it's either ES here over Z total, or basically this is ES and opposite of Z total, which is 1 over Z total, is nothing but the admittance, right? So you can use this, this is Y total, that's the total admittance times this, or this times Z total to give you that source current, or the total current. And since it's parallel, this current is going to be divided between the 3. So next step is to find IR, IL, and IC. And we can either again find them directly by Ohm's law. For example, IR here is nothing but the voltage across R, which is nothing but ES because it's parallel, so it's the same voltage everywhere. This voltage VR is nothing but ES, so it's ES over R, 5. For the IL, it's going to be ES over J10. For the IC, it's going to be ES over minus J20. Don't forget the J. Remember, these are Euler numbers and they have magnitude and angle to the calculation. This is one way. Another way, we can use a current divider rule. Once we know this IS, we can apply current divider rule to find any of the 3 individual currents. Now, we need to make sure, we need to check that whether our solution is correct or not. So if you add them up, IR, so I'm just going to add IR plus IL plus IC, you should get I source. And once this is approved, then your KCL is checked and your solution is correct. Check, right? So that's IR. Okay. What else? Also, you should be able to draw the Phasor diagram, which is all the currents and the voltage. That's the Phasor diagram. What else? We should be able to calculate the power that is consumed in the resistance. So the power consumed here is P, and the power stored here is a QL. And the power stored here is a QC, right? And remember, these two powers are opposite to each other in sign. This one is positive, this one is negative. That's the real power. This is in watt, this is in var, this is again in var. If you add them up together, then you will get apparent power S, right? And S is B plus minus J Q. That plus and minus depends whether you're talking about a total of QL or a total of QC, as we will see in number 4. So this is basically what we've done in parallel circuits, right? Yeah, you can pause the video anytime, guys, to take notes or just take a screenshot or whatever, right? But we have done all of these before the midterm. So this was number 3, and then after that we discussed the individual powers in single phase AC circuits, right? And here, just a quick review. Remember, we said we have different or maybe 3 types of power here. We talked about them, right? And we made a table, and we talked 2 or maybe 3 examples on this. P, which is the real power, or a true power, or average power, or watt power, or active power. That's the power that is typically in our circuits consumed in the resistive element only. And this is in watt. So this is in watt, right? Okay? And how do we calculate it? As we learned from circuit 1 and also from the beginning of circuit 2. That's a real power. So you have to say it's I times R, but this is I squared, and it's not any I. It is the current across that resistance. The current across a certain resistance square times the value of that resistance will give you the power that is consumed in that resistance. You cannot take the source current. No. The source current could be correct if it is only series circuit. But make sure it's always the current that is inside that resistance, that flows in that specific resistance. Now, another method or another formula is V squared over R, right? And again, it's not only any voltage, no. It's the voltage across that resistance, V square over R, or V times I. And again, not any V, not any I, no. It's the voltage across that resistance and the current which is flowing through that resistance. If you multiply them together, you will get the power that is consumed in that resistance. Okay? Q. A Q could be QL or QC. So this is the reactive power that is absorbed by the imaginary element or the inductance of the inductive impedance or capacitive impedance, XL and XC, right? And remember, these are imaginary numbers, so we typically use JQL minus JQC. And in order to find the Q, we can use the same formulas here basically, but definitely not for R, because the Q is not related to R. Q is related to either XL or XC. So in general, let me call it X. So Q will be I square times X, not I. Which I? Not any I. The I that flows through that X, whether it is XL or XC, or V square over X. Again, not any voltage, no. The voltage across that X, right? Or V times I. Again, not any voltage or I. It's voltage across that X and the current flowing through that X, right? Okay? Okay. Alternatively, we can calculate the real power that is supplied by the source, PS, by multiplying the magnitude of ES, that's the supplied voltage, and we're looking for the RMS magnitude here, no angle here, right? Times the current IS, this is the current supplied by the source, times the power factor or cosine of theta ES minus theta IS, or theta of Z total, typically, right? That's basically the power factor. If you do this, this will give you the supplied active power to the circuit. For the Q supplied by the source, it's gonna be ES, only the RMS value, no angle here, IS, and instead of cosine, it is sine of theta, ES minus theta IS, right? This is the total reactive power supplied by the source. If you add them up, and remember, we cannot add them directly because this is a scalar number, this is a real number, this is an imaginary number. So you have to add them like this. It's BS plus minus JQS, right? This will give you the total apparent power in volt ampere. So apparent power is a complex number. That's why we also call it a complex power. You want to convert it to magnitude? The magnitude of this is just BS squared plus QS squared. Right? That's the magnitude. If you want to bring the angle is basically tan inverse of the imaginary part over the real part. Another way of calculating the magnitude is typically by saying it's the magnitude of ES times the magnitude of IS. This will give you the magnitude, or sorry, the RMS value of the apparent power. This is what we have covered so far until the midterm. So everything until here was about single phase AC circuit. Single phase AC circuit. When power supply connected to the load, and that load could be connected either in series or in parallel, or a combination of series and parallel, but in this course, combination is not covered, right? So I'm going to pause the video now for 1 minute, take a break, and then we'll come back to talk about the three-phase AC circuit, which is lecture 6, the next session, or this session of week number 8. Thank you. Okay, welcome to part 2 of this session. And this part I'm going to go a little bit slowly because it's a new topic for you. So we're going to be talking about the three-phase AC circuits. What we talked about in part 1 was basically about what has been covered before. So it wasn't new for you. It was just a quick review. Now, again, what has been covered so far in the course was all about single-phase AC circuits. Single-phase AC circuits, so it's basically, that's a source, and this source here is connected to a load. Let's say it's an RL load, right? So this is a resistance, that's XL. Don't forget the J, so it's JXL. That's your source, it's a plus, minus. Typically we don't put plus minus inside because it's an AC, so it looks like a sine wave, so that's a sine wave. I'm gonna call this one plus minus ES, right? Okay. You see it's only one source, and that source is supplying power to load. This load could be RL, RC, RLC, it could be series, it could be parallel, it could be combination of parallel and series together, right? Let's say now this is what we have. This is a single phase circuit. Single source supplying single load, right? Okay. Now I'm gonna do something here. I'm gonna bring other two sources and connect it with the existing source. So I'm gonna call this source again ES, and this source is an ES, right? Okay, sorry. Okay, and now it becomes three sources, and I'm gonna do the same here in the load side, right? So let me take more space here so we can make an accurate drawing. Okay, so that's here. Let's say this is your load. That's RL, right? So far now, what is being drawn by a red color is a single phase. So that's a resistance. This is JXL. One load. I'm gonna bring another two load, R, with JXL. So this is JXL. And the third one, R, with JXL, so this is JXL. So typically these three now are identical. They are the same, RJXL. We call this balance load. Balance load means they are the same. RJXL, R plus JXL, R plus JXL, R plus JXL. JXL is just an example. It could be JXC, it could be JXL with JXC in series. This could be parallel. This could also be parallel, right? This is just an example. So basically this load now is same as these two loads. We call this balance load. And in this side, which is supply side or source side, or typically substation sides, for us it's a source at the end. The three sources here are the same in magnitude, but they are different in the phase shift, as we will see. So now let me put alphabeticals here. Let me use alphabeticals to make everything easy for us. So I'm gonna call this point here small a. That point is B, small b, and that point here is a small c. Okay, right? Okay, it's just name. Here I'm gonna call it capital A. That one is capital B, and that one is capital C. These three points, right? Now let's connect. A now is connected to A, right? Sorry. So A now is linked directly to A. This was our original single phase circuits, and now we are bringing another two single phase circuits. We connected with the existing one, right? So let's connect B with B. So this is gonna be something like this. That's B with B, right? And let's connect C with C. So this is my C here. And remember, this is not an intersection, it's just a jumper. And bypassing this, so there's no connection here, C with C, right? So B with B, C with C, okay, and A with A. Now, what you see in front of you is called a three-phase circuit. A three-phase source side connected to a three-phase load side, right? And these three sources are the same in RMS values, but the only difference is the phase shift between them, as we will see. Then we call it balanced sources. And these three loads are copy-paste of each other. Only the same values of R and the same values of XL. So we call it balance load. If I change, let's say this XL now, for example, is J4, this XL is J4, and this one is J4, right? Okay, and R is 2 ohm. This is now a balanced load, the same values for the three load. If this one was different, like not 4, it was like 6 with 8, for example. Now this branch is different from the other two branches. Now it's no longer balanced system. This is unbalanced load. This scenario here is unbalanced and it's not a part of this course, so forget about it. So we will only stick with the balanced load. So balanced load means they are all the same values, right? So let's put them again. This is R JXL, this is R JXL, and this one is R again JXL, right? Okay. Okay. And as you can see, this source is supplying the load here. This source is supplying the load here, and this source is supplying the load here. We call it a three-phase system. Let's think a little bit about the shape. The shape of the source size and the shape of the load size in terms of connection. If you focus, you will note that this connection is similar to what? Does this remind you of anything? And again, this connection is similar to this, right? Right? Let's guess. Does this remind us of any alphabetical? That's actually opposite of Y, right? Y. So it's typically now connected in Y, right? This is opposite again. So I can play with the connection to make them upside down, so it becomes Y connections. So in other words, if you see such a connection shape, then this side is Y connection, right? And this side again is Y connection. Y connection means what? Or a star connection. A star connection means the three branches have one point in common, which is this, right? And the other 3 points are connected to the sources. The same thing here in the source side. The 3 sources have one point in common here. They are linked in that point. They are shorted in that point, right? And I'm going to call this point here capital N, which is a neutral, and this one is a small n. This is just a convention that in the source side we use capital letters, in the load side we use small letters, right? Okay. So now I will have to change the names according to the alphabeticals here. So the voltage from here to here is going to be E capital AN, right? This voltage is going to be E, can you help me? This is going to be BN, and this voltage is going to be between C and N. So this is capital CN, right? If you want to put a sign, so this is a plus minus, this is a plus minus, just for the convention of the source, right? Okay, that's the voltage. Let's do the voltage in the load side. Now, typically in the supply side or in the source side, I use E. When I go on the load side, to distinguish between them, I'm going to use V for the voltage. So from here to here, this is a plus minus VAN. From here to here, across the load, this is a plus minus VBN. And from here to here, again, so plus minus VCN. Right? Good. Okay. And this is connected here. So Right. Now, what about the currents? That's the source, that's the load there. So there will be a current out of the source all the way to the load. And this current here, I'm going to call it I from capital A to small a. So let's call it here I small a. Right? You want to call it I capital A, it's fine. At the end, it's the same point actually. This is nothing but a wire. Now typically in real life, there is some transmission step here, but it's not included in this course. So our basic simple circuit here is supplied directly to the load, right? So this is just a wire with negligible resistance, okay? So there is a current that goes from this A to that A, and this current now is going to that load. So what will be the current in that load? Again, the current here is I small a, which is nothing but this current because it's series. This source now is series with this load. So it's the same current. IA, right? Good. What about the other source? Now, there will be a current here that goes out of this source, and I'm going to call this current because it comes out of B and it goes to the small b. Let's call it IB. And that current, as you can see here, it goes out of this source all the way to this load. So the current in this load is IB, which is nothing but this current. Right? The third one, we have ECN. So there's a current that goes out of this, and this current now is IC. And that current goes all the way to this load, IC. So the current in this load is IC. Okay? What else we have to identify here? Yes. Now, what will happen here when these three currents will add to each other? So there is a current that is coming from here, that's IA. There is a current that is coming from here, that's IC. As you can see, IC. And there is a current here which is IB. They will come at this point, and the summation of the three currents will be here. I neutral. Right? This is just a convention, right? I in neutral. The sign here is just a convention. Now, if it is a balanced system, and we said in this course we're only covering the balanced system. Balanced system means this load is the same as this load, is the same as this load, right? This source is the same as this source, is the same as this source in magnitude, not in the phase angle, in the RMS value only. This is balanced system. In balanced system, the summation of this current and this current and this current, which is equal to IN, will be 0. They will cancel each other here, and theoretically there should be no current in the neutral line. So theoretically this is 0 if it is a balanced system. We will solve examples and see. Right. What else we have to define here? Right, I'm going to define another voltage here between this point and just for you to see everything. So let me go here, right? Let me just put it here. So let's move this one a little bit. IN is here. So let's say this is IN. And typically it is going to be 0 in balanced system, right? Now, there is a voltage between this line, which is A, and a voltage between this line, right? The voltage from here to here, right, is V A, right? You see, that's A. This line is A here. And this one is B, so it's VAB. And the load side. You want to take it in the supply side again from here. You see this voltage VAB there is nothing but it's the voltage from here to here, right? I'm following up, it's the same voltage, the same lines, right? So I'm gonna call this one also EAB. Right? They are the same. Okay? So you can either call it VAB based on the load side because the convention is to use V in the load side, or EAB because the convention is to use E in the source side. Right? In this circuit, they are the same. There is another voltage which is from A to C. From this line, the red one to the blue one. And I'm going to call this voltage V small AC, right? Or E capital AC. And again, it's line to line voltage. It's from line A to line C. That's another voltage, right? What else? There is a voltage that is between line B, this is line B, the red one, and the blue one, which is line C. And we're gonna call this voltage, that's voltage here, is EBC. If it is close to the load side, it's the same voltage, but we're gonna change it to VBC. Right? It's just a matter of name. As I said in the beginning, it's a convention that we use E in the source side, V in the load side. But here they are the same, right? They are the same. They are connected in parallel, right? What is the key point here? The key point here is to identify two types of voltages. The first type is line to line voltage. Right? And the other type is called line to neutral voltages, or simply we call them phase voltages. For simplicity, they are known as phase voltages. Right. What are the line-to-line voltages? Okay, the line-to-line voltages is the voltage difference between any line and another line. Right? That's line-to-line voltages. So what we have? We have EAB, a voltage from this point to this point, from this line A to this line B. That's EAB. What else? We have EBC. There is a voltage between B, line B, and line C. What else? A voltage named CA, which is the voltage between this line, the blue one C, and this red one A. That's ECA. Note that this voltage is line to line voltage. Right? Line to line voltage. Typically we call it line voltage. Whenever we say line voltage in circuit, it means line to line voltage. Okay? Now let's think. If you follow me here, the voltage from this point to this point, which is this, is just a line, which is basically this. I'm calling it EAB, right? Because it's between point A and B here. Now let's continue. And the load side, it's the same voltage, right? Between A, small a, and small b, right? So it's the same, they are parallel. That's why I'm saying EAB is equal to VAB. So the line voltage from this side, the source side, is the same as the line voltage in the load side. So I can call this one VAB, this one VBC, this one VCA, right? Okay, this is line to line voltage. Okay, the other type of voltages is phase voltages or line to neutral voltages, phase voltages or line to neutral, right? Which is the voltage between this line and the neutral, which is EAN. The voltage between this line and the neutral, which is EBN. And the voltage here, which is ECN. So the phase voltages are EAN. Note that N is always there. EBN, ECN. This is in the supply side, right? But if you follow me here, this voltage, which is EAN, is in parallel with this voltage, which is VAN. They are in parallel, right? And the load side. So this means EAN is equal to VAN, VBN, VCN. Okay? We call it phase voltage or line to neutral, 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 line to neutral voltage. So far we have defined two types of voltages: line to line voltage and phase voltages or line to neutral voltages. And typically this line to line voltages is always higher than the phase voltages, and there is a relation between them, as we will see, right? Before I write up these relations, we'll take examples later, but before I write them up, we said now this circuit in front of us is Y connection here and another Y connection here. So I'm going to call this one Y circuit. Y circuit. Right? So this is Y connection, Y load side connection, Y this side, Y this side circuit. There's another type of connection as we will see in part 3. But in this part, this is Y. The source is connected as Y, the load is connected as Y. There is another terminology for that Y, which is star. So whenever we say a star connected, it means Y. Star is Y connection. That's just another term. Okay? Right. Now, what is the relation between these three phase voltages? Phase voltage A, phase voltage B, phase voltage C. Here, this is in source side, load side. Phase voltage V, A, phase voltage B, phase voltage C. Phase voltage in the load side is equal to the phase voltage in the source side in this connection. Line voltage from here to here, from line to line, right? And the load side is equal to the line voltage in the phase side, right? But what is the difference between the individual's phase voltages here and the individual line voltages? This voltage is phase A, this voltage is phase B, this voltage is phase C. They are balanced system. They are in balanced system, which means they have the same magnitude, and I'm going to call it E, the same RMS, for example, 120 volt, 120 volt, 120 volt. They are always the same RMS value in a balanced system. But the angle is different. So let's say this angle is 0, for example. The angle here starts by 0. Then what will happen? VBC, VCA will have the same RMS value again, but the angle will be shifted. There is a shift angle here, and there is another shift angle here, right? Okay, so just to make space so I don't confuse you, let me put AC and this here, right? Okay, that phase angle shift depends on the type of phase sequence. Phase sequence. So let us define the phase sequence. In this course, we will always assume that our phase sequence is positive sequence. So in the question, phase sequence can either be positive sequence or negative sequence. Positive sequence or the same as A, B, C sequence. It's the same, right? Either we call it positive sequence or A, B, C sequence. We're going to be focusing on this sequence. There's another sequence which is negative sequence or A, C, B, right? Let me clarify them. Let's say now this is the origin point, and let's say now this is now your vector of EAN, right? That's EAN here. So EAN here has a RMS value, a length, and the phase angle here, or it's at x-axis, so the phase angle is 0. Now, the other two phase voltages, which is BN and CN, will have the same length exactly, the same length of this, but now it's at 120 angle shift. 120, this is 120, this is also 120 shift, right? So I'm going to call this one B and this one C. This is positive sequence. Imagine you are standing here at the marker side here. You are the marker here, right? And these three are rotating. The first vector will pass by you is going to be EA. And then it will be what? They are rotating, right? Now the three vectors here are rotating anti-clockwise. So EAN will pass by the marker first, and then BN will come, and then CN will come, right? That's why we call it A, B, C sequence. A, B, C sequence, or positive sequence. Based on this sequence here, if the angle of if the angle of EAN, forget about this, we'll come to it later. If the angle of EAN is 0, it is at x-axis, and the magnitude here is, let's say, V. That's the RMS value, and this is the angle is 0. Now, the other two phases from the assuming positive sequence will be again the same RMS value, but the angle here is no longer 0. The angle here is minus 120. Can you see that? If this is AAN, it is at 0, and then BN will be minus 120. What about CN? It should be clear for everybody now. CN will be again the same RMS, but the angle is what? Plus 120. Right? So that's CN, so the angle is plus 120. Okay? Somebody else might write this one as 240. It's again correct, right? Minus 120 is nothing but 240 degrees. So this is how we write them now. The three phase voltages have the same RMS value, but they are shifted by minus 120 plus 120. The same idea goes for the line-to-line voltages. Line to line voltages have the same RMS values, but there is a shift angle between them, right? So, let's say this angle here is theta 1. Then what will be this angle? It will be this angle, which is ABC here. It will be theta 1 minus 120. And this will be theta 1 plus 120. There is always minus and plus 120 based on the assumption that our sequence is A, B, C. That sequence would be just accepted. Right? Now, so this is line-to-line voltages. This is phase voltages. What is the relation between line-to-line voltages and phase voltages? One relation. If you find phase voltages, you should be able to bring line-to-line voltages, right? I'm gonna write this for you now. Right. So line to line voltages in general is E line with another line. So it's AB capital, CA capital, BC capital. That's line with another line is always and always higher than line to neutral voltages. E line to neutral is one line with the neutral. So it's A with neutral, B with the neutral, C with the neutral, or simply we call it E phase. E phase, which is same as E line to neutral. What's the relation between them? If you know E phase, which is E line to neutral, you need to multiply it by root of 3. Now it becomes line to line. And if it is positive sequence, you will have to add a phase shift of plus 30. So if we know E phase, we multiply it by root of 3, you will get line to line voltages, right? Remember in our lab, in your lab, you have two standard of voltages from the power supply. Is 120 volt or 208 volt. 120, you get it usually from 1 with N, 2 with N, or 3 with N, right? That's line to neutral. But 208, you get it when you connect it 1 to 2, or 2 to 3, or 1 to 3. That's line to line. If you check the relation between them, it's square root of 3. 120 times root of 3 will give you 208 voltages. This is what we have in the lab. That's the relation. This is line to line voltages is equal to root of 3, which is 1.73 times line to neutral or phase voltages. This is a very important relation. Right. What about the currents? The currents, now we have the drawing of Y-to-Y system. So, okay, let's continue. There was just a small issue with the recording. Right, so what we said that for the Y-to-Y connection here, typically for the Y connected load, that's the key relation between the voltages. The line-to-line voltages is equal to root of 3, 1.73 times the line to neutral or the phase voltages with a 30-degree phase shift based on the assumption that our sequence is positive sequence. What about the currents? What is the relation between the line current and the load current? So let me draw it quickly. This is a load, so this is it. This is a load, that's the other load, that's the third load, right? Okay, and here, this is Z, Z, Z. Remember, this could be RL, RC, RLC, series, parallel. In the previous circuit, we draw RL in series, right? And here we have a source. So these are 3 sources. Right, so let me just draw them quickly. So here we have this goes to here, that's A, and this goes to B here, and this goes to C, right? Okay, so let's check the current. This is the current, this is the phase current. Remember, this point is in neutral, so this is IN. I'm going to call it IAN, small n, right? The current here is capital A, this is N. And there is a current in that line. This current here is the load current. You see that current that goes to the load, inside the load directly. Or we call it small a to n current, IAN. Or phase current basically. So it's all the same, I phase, IAN, or we can call it I load. It is the current that goes inside the load. This current here is the current that is in the line, line A, right? That flows here. And the same thing with this current. There is a current here that goes to this load, and this current is I, what is this? That's C. It is CN that goes here, and there is a current here which is I, what is this? That's BN, right? And again, these 3 currents are going inside the load. They have the same RMS values, but again, they are phase shifted by plus 120, minus 120 based on the sequence of positive sequence A, B, C, as we will see in the example later, right? But note something here. This current, which is phase current or load current or line A to neutral current, is the same as this current, right? Isn't it? It's just one current that goes from this source all the way to this load. So this current, which is load current, is equal to this current, which is line current. They are the same. So in Y connection load, the line current is equal to the load current. They will be different in another connection later, but in this connection, as you can see, it's the same. Line A current is the same as load A current. Line C current is the same as load C current. Line B current is the same as load B current. So what's the conclusion here? For the Y connected load, for the Y connected load, for the star connected load, Y or star, it's the same. The line to line voltage is different from line to neutral voltage, is different from phase voltage. The line to line voltage is √3 times phase voltage with a phase shift of +30, assuming that the sequence is positive sequence. What about the current? The line current is nothing but the phase current, which is load current. They are the same. There is no difference as we just saw in the drawing, right? So these are the two important relations that we need to know before we can solve any Y-connected load system, right? So I'm gonna have to stop here to take a little bit of rest for you guys, and then we will come back in part 3 to do one example, one calculation example of Y-connected load, and then after that we will talk finally about the second type of a connection of a three-phase connection load, which is going to be delta connected load, and again we'll take one more example of that, right? So see you then after taking a rest. So, morning guys. So in this part we'll do examples. This is one example of Y-connected load. This is Y shape, a three-phase Y-connected load. It's a balanced load. That's the load per phase. The load per phase is 6 plus J8 ohm. Now, which means that this is a series connection typically between resistive part and, since it's a plus, that's JXL, an inductive part. And these are identical load because it's a balanced load. Now, what is given here is the voltage. This voltage, which is from line A, that's line A, with the neutral, is given, right? And now this side here is the source, typically, right? So what we have here is this comes from the source. The source in this box, there is a three-phase. In that box, there is a three-phase, let's say Y connected, because typically it's a Y connected in source side, source, right? Now, as long as this one is known, it's given in the question, we don't need to worry about the details of the source size, because here we are mainly focusing on the calculation in the load side, right? Okay, so I'm gonna take this one out just to save space. So that's your load, Y connection load. This voltage is given. Now these are the requirements for the questions. Now for the Y connected load here, you have to determine the following. Number one, the load voltages. The load voltages basically are what? The voltages across every load, right? So this voltage here is VAN, this voltage here is VBN, and this voltage here is VCN. Okay? So basically what we are looking for here, the load voltages is we want to know VAN, VBN and VCN in the load side. Then the line to line voltages number 2. Line voltages is between the lines, right? You see the phase voltages here are between the line and the neutral typically, AN, BN, CN. So neutral is always there. That's why it's also called line to neutral voltages, right? Line to line voltages is between the lines themselves, right? So what we are looking for here is the voltage between line A with line C, the voltage between line A with B, the voltage between line C with B. So these are basically here the voltage AB, the voltage between B and C, and the voltage between C and A. Line to line, line to line, line to line. It could be ABC or it could be 1, 2, 1, 2, 3. So it will be 1, 2, 2, 3, 3, 1, right? Or 4, 5, 6 as we have in the lab in the stations, 1, 2, 3 or 4, 5, 6. These are basically our lines, just line 1, line 2, line 3, or we call them here A, B, C. These are the lines, line 1, line 2, line 3. So we want line to line voltages here. This is line to line voltages. Then the load currents. The load currents are the currents flowing in the load itself. So it's basically this current goes to this load, and there is a current going in that load, and the current going in that load, right? So what we call these currents basically, this is IAN because it goes from A to N. This is IBN, it goes from B to N, and this one is ICN because it goes from C to N. So what we're looking for here is IAN, IBN, and ICN. Okay? These are the load currents or the phase currents. Then the line currents. The line currents here are the currents which are flowing in the line. So this is current, line current of A. I'm gonna call it IA, right? This is the current in C. So this is IC, and this is the current in B, which is IB, and it's clear for everybody that these currents are nothing but at the same as load current because it's just one line, right? It is series, so they are the same, as we will see when we solve the examples. So the line currents here are basically called IA, IB, IC. Number 5, the neutral current. So as we said in the last part, when we add them up, when you sum these 3 currents, the result is the current in the line. So there is a current here, let me call it IN. That's line current, okay? Which is a summation of the 3. So what we're looking for here is IN, and IN is nothing but IA plus IB, right? Plus IC, or we call them IAN plus IBN plus ICN. But in Y connection, you can also say IA, IB, IC because they are the same, as we will see. And finally, the active, reactive, and apparent power absorbed by the load. Here the load is a resistive part with an inductive, which means resistive part will absorb real power from the source. Inductive part will absorb or will store reactive power from the source, and when you add active to reactive power, the result is apparent power. So let's solve these examples. Now remember from last part, our sequence here is ABC, positive sequence. So if this is vector A, vector B will be lagging behind by 120, while vector C will be leading ahead by 120 degrees. So we're going to use this one now to bring the phase shifts between the 3 phases. Okay? So let me start by number 1, the load voltages. Okay? So the load voltages, that's number 1. The load voltages we are looking for VAN, VBN, VCN. Okay? And we'll continue in the next part just to save the time of every part. Okay, so let's solve the example here. So number one, we want the load voltages. So we gotta start by VAN. So basically VAN is given and it is 130 volt angle of 0. Now once one phase is given, you will be able to find the other two phases. That's fault. We're looking at our voltages. So VBN, it's a balanced system. So VBN, VCN here will be the same. RMS value 130, 130, but now there is a phase shift between the three. This is fault, and the phase shift is obtained from here. If this is vector A, this will be B, and this will be C. So vector A here, as you can see, is given at angle 0, right? So vector B will be lagging behind by 120, and vector C will be leading behind by 120. So it's typically this angle, which is 0, plus, sorry, that's B. B is here, it's lagging behind. It's not a plus, that's minus. 0 minus 120. That's for B. For C, it will be 0, which is this, plus 120. Or typically minus 120 plus 120. This is done. Part 1 is done. The load voltages now is known. So the three-phase load voltages have the same RMS values, but phase shifted by minus 120 plus 120. This is number one. Number two is the line voltages. Now we need to recall the relation between line voltages and phase voltages in Y connection, assuming positive sequence. Remember from the last part, E line to line is always greater than line to neutral, is equal to root of 3, 1.73 times E line to neutral, or phase voltages, E phase, and there is a phase shift between them by 30 plus. This is an ABC sequence Y connection. So let's apply the formula here, right? So I know that load currents. I'm gonna bring now the line currents, which is V between AB, VBC, and then VCA. Let's bring the first one with respect to the line to neutral here. So it's typically from the formula there, it's root of 3 times 130, and there is a phase shift. The phase shift, this is 0 already, plus a phase shift of, so this one is 0, plus a phase shift of 30 from the formula here, right? That's the line-to-line voltages. Once we know this, we can bring the other two line-to-line voltages. They will have the same amplitude, the same RMS value, 130 times root of 3, 130 times root of 3. The only difference is that now, remember, it's a three-phase and it's an ABC sequence, so there should be a phase shift of 1 plus minus 120. So this will be 30 from here minus 120. And this will be 30 from here plus 120. Volt. These are the line-to-line voltages in the load side. So number 2 here is done. Number 2 here is done. Okay? Now, load currents. The load currents are the currents that flows inside the load, which is IAN, IBN, ICN. Typically here, what we're going to have to do simply is to apply Ohm's law. Right? So, I'm going to take this one out because I don't need it for calculation of the load current. I need this for calculation of the load current. I need the load voltage to calculate the load current. So just because I don't have space here, let me take this one out. Right? And this will be number 3. So of course you can pause the video anytime and take the notes. Number 3 is the load currents. So what will be IAN? Ohm's law. What will be the current in this load here? It's basically the voltage here, which is VAN, over Z phase, right? That's Ohm's law. Okay? The voltage over Z phase. Okay, so this is gonna be the voltage VAN plus Z phase. And this one is VAN is, where is VAN? That's VAN. 130 angle 0, 130 angle 0 over Z phase, that's Z phase, which is 6 plus J8. Remember, this is rectangular. To do division or multiplication, we need to convert it to Polar. So if you convert this one to Polar, Z phase in Polar here, 6 and 8, square root of 6 square plus 8 square. This is going to be square root of 100, so this is 10. And the angle is 6 and 8, so this is tan inverse of 8 over 6. This should be in the first quadrant. If you do it by your calculator, tan inverse of 8 over 6 will give you 53.13. That's the Z phase in polar form. So this is over 10, 53.13. Right? This is IAN. So this is IAN and it will be equal to 130 over 10. So this is basically 13 angle of 0 minus 53. Remember, or you shift this one out, it becomes minus 53.13. Right? Ampere. Once we know IAN, IBN will be the same amplitude, ICN will be the same RMS value. The only difference is that there is a phase shift between them. Minus 120 plus 120. So IBN will be 13 minus 53.13 minus 120. ICN will be 13, the same RMS value, minus 53.13 plus 120. Don't forget this. This is ampere, right? Okay. So these are the load currents, number 3. The load currents. Number 4 is very straightforward. Number 4, which is the line currents, IA, IB, IC. It should be clear for everybody that IA here is nothing but IAN. It's the same current. IC here is nothing but ICN. IB is equal to IBN. So the load current is equal to the line current in Y connection topology. Okay? So IAN here is already equal to IA. IBN is nothing but IB, and ICN is again equal to IC. So the line currents are equal with the load currents. Okay? Let me take this one out. Erase it so we have some space. So number 3 and 4 is done. The 3 and 4 typically here is done. Because line current and load currents are the same. Number 5. The neutral current. The neutral current is the summations of the load currents. So that's number 5. Let's do number 5. Number 5 is the summation of the load currents. So the load currents IAN plus IBN plus ICN should give you I neutral when you add them together. This current plus this current plus this current will go here to IAN, right? But again, remember, these are now already obtained in polar form, and it's not easy to add them in polar, so we always have to compare them to rectangular. As I advised you before in the previous classes, we always try to get the results in both forms, rectangular and polar, so that whenever you need any one of them, you can use it directly. So if you convert these 3 from polar to rectangular, let me put them first in polar. IAN is 13 minus 53.13. IBN is 13 and the angle is minus 53 minus 120. So this is going to be minus 173.13 plus, what about ICN? ICN is again 13. What about the angle? The angle is minus 53 plus 120, so this is gonna be 66.87 almost, right? This is in Polar now. So let's convert everyone from Polar to rectangular by your calculator or by the formula that everybody should know. 13 cosine of the angle plus J, 13 sine of the angle, right? So when you convert them, when we convert them, this will be 7.8 minus J, 10.4. Just do it by your calculator and check. And this one, 13 minus 173 cosine sine. So it will be minus 12.9. Which quadrant is this? This is going to be in the third quadrant. Minus 173 in the third quadrant. So this is minus again G, 1.56. And here, 1366. This is in the first quadrant. And so it's 5.1 plus J, 13 sine of 66.7, it's almost 12, or it's very close to 12, let's say 95, 96. If you add them together, real with real, 7.8 minus 12.9 plus 5.1, that's 0. Minus 10.4 imaginary, minus 1.56, this is almost 12, plus 12, it is 0. So the result here is confirmed 0. Neutral current should be 0 because it's a balanced system. That's why when you add them together, they will cancel each other. The result of IN is 0. Number 5 is done. Finally, active, reactive, and apparent power of absorbed by the load. So every load here has a resistive element and inductive element. The resistive element typically consume active power, P, watt. 8 here, which is JXL, will absorb or store reactive power, Q, right? So this is now which question is this? Number 6. So this is number 6. So remember, active power, B, you have so many formulas. Now one common formula here is to say I square times the value of the resistance, right? This is from circuit 1 and even from the beginning of circuit 2 until for that single phase AC circuits. But again, which I? Not any I. The I that flows inside that resistance, which is typically here, the resistance is here. If you open this one, this is nothing but a resistance with inductor, right? So this current here, IAN, is the current goes to the resistance, right? So I'm going to call it IAN square times R, right? And this is RMS value only. We didn't consider the angle here in the calculation. But I square times R is the power for a single phase circuit for one resistance only. Here we have 3 identical loads, 3 identical resistance, 1, 2, 3. So in order to bring the 3-phase power, typically this is a 3-phase, we will have to multiply everything by 3. This will give you the 3-phase power, right? This is one way. Another way is P of the 3-phase is to say square root of 3, this is fixed in the formula, times E, not E, let me use V here because it's in the left side, V, line to line, which is VAB, right? Or since we are using phase, let's stick with phase for you, right? VAB. Let's stick with phase. Let's stick with phase. So we didn't get confused. This is a 3 times phi phase. Phi phase is VAN. Here, that's VAN. Times IAN
times cosine of theta z total, or theta of this voltage minus theta of this current, which is equal to the theta of the z total here, right? Which is power factor. Cosine of theta z total is again a power factor. This is another formula. If you do the calculation, this one will be 3 times 13 square. The resistance here is 6, right? And here it is 3. What is VAN? VAN is 130. What is IAN is 13. What is cosine theta z total? Theta is this. Cosine 53.13 is 0.6. Is 0.6. If you do the calculation, both will give you almost 3 times 6 times 13 times 13. This will be almost 3 kilowatt. 3 kilowatt. That's the three-phase real power consumed in the resistive part of the load here, right? Okay. Now, let's continue here. Let's continue here. For number 6 again. So that's the three-phase real power. Let's continue here. Now Q, reactive power absorbed by the or stored by the inductive part of the element. So it's typically I square again times XL, right? In the calculation here, I square times XL. This is for single phase. This is for one inductive only. But here we have 3 identical inductives, so it will be times 3. This is the total 3-phase reactive power. Okay? Which is 3 times I square is 13. That's again IAN. It's the load current, and it's the same 13. We don't consider the phase shift here when we do the calculation of power. Times XL, how much is XL? That's XL, which is 8, right? Or by using the other formula, Q3 phase is 3 times V phase, which is VAN, V line to neutral, times I phase, which is IAN. This is the RMS value, this is just for the absolute value. I don't consider the angle. But instead of cosine, for B here it's cosine, instead of cosine it will be sine of theta z total. Right? So this is a 3 times 130 times 13. Now sine of theta of z total, if cosine is 0.6, sine will be 0.8. 0.8. Right? And if you do the calculation here, 3 times, sorry, I missed the square here, remember the square here of the cal. If we do the calculation here, this will be almost 4 kilowatt. So 4 kilo, no, not kilowatt, sorry, that's a Q. That's a Q, guys, right? That's not kilowatt, watt is for the B, is for the real power. That's the reactive power, so kilowatt. Kilowatt. Okay? What else we can bring here? Finally is that's active, reactive, and aberrant power. So aberrant power here will be what? Aberrant power is S. Remember, S is a complex number. It's a plus P plus J cube. So this is a 3 plus J 4. Kilo, everything is kilo, remember the kilo, right? If you take the magnitudes, that's square root, so S is square root of a 3 square plus 4 square. This is going to be 5 volt ampere. That's volt ampere. It's S volt ampere. Volt ampere, right? What about the power factor? Let's say power factor. How do we calculate the power factor? Power factor is actually here is either cosine of theta voltage minus theta current, or cosine of theta of z, right? Or it's B over S. If you apply any one of these, B over S, how much is B? B is a 3. Let me apply this. B is a 3 kilowatt, S is 5 kilovolt ampere. This is gonna be 0.6 power factor. Is it lagging, leading, or unity? What do you think? We take a look to the load here. That load is a resistance in series with inductor. Inductor means lagging. So this will be lagging power factor. And with this one, we reach to the end of this example. That's Y connected load example. In the last part of this lecture, we will solve another example, but with delta connected load. See you in the next part. Okay, so that's another example, but this time it's again three-phase balanced load, but this time they are not Y connected. This is delta connection. It takes the shape of delta, right? Or basically a triangle. That's delta connection. Load 1, load 2, load 3. These loads are identical. Every load here is 4 plus J3 ohm, which means inside we have a resistive element and again inductive element, and they are connected here in series inside, right? Okay. So this is delta shape. We're gonna try to bring the same requirements that we did for the Y connected load. This is line A, capital C, capital B. This point is a small a, this point is a small b, and that point is a small c. This is the load side here. So the voltage from here to here across this load here is VAB. This is now the load voltage, the voltage across the load itself, right? The voltage here is between A and C. So this is VCA, right? The voltage here is between B and C. So this is VBC, right? So first, the load voltages. The load voltages here are VAB, VBC, and VCA. Okay? That's the load voltages. Let me make them clear. The load voltages here are VAB, VBC, and VCA. The line voltages or line-to-line voltages are from line A to C, line C to line B, and line A to line B. So it's typically V here, AB capital, VBC capital, VCA capital. But one may notice that this line-to-line voltage is nothing but the load voltage. They are the same, right? This voltage between A and C is in parallel with this load voltage between small a and small c, right? The same thing here. The voltage between line C and line B is the same as the voltage between C and B. They are the same. They are parallel, right? And this is the beauty of delta connection. So in delta connections, for delta load, E line to line is nothing but E load. There is no difference between them, right? In Y connection, they were different. In Y connected load, E line to line was always greater than E load by square root of 3 and a phase shift. Here they are the same, right? So line to line voltages VAB, VBC, VCA, all capitals are equal to the small or load voltages here. Then the load currents, the current that goes inside the load, that flows in every load. So there is a current here, and that current is from A to B, so I'm going to call it IAB. There is a current here, and this current is IBC, from B to C, and there's a current here in that load, and this current is ICA, right? This is the load currents. The current flows in every load. We call it load current. So we're looking for IAB, IBC, and then ICA. The line currents, the current that flows in the line. So this current is I capital A. This current here is I capital C. This current is I capital B, right? And you may notice now in delta connection that the line current is different from the load current. When it comes to this buoyant, it's not equal to this current or this current. In Y connection, the line current was equal to load current. In delta connection, no, they are different. So, what's the relation between them? Assuming positive sequence ABC again, the I line current is always greater than the load current. So it's root over 3 times I load or I phase. And there is an angle shift here in ABC sequence by minus 30. So this is the formulas that we're going to use for delta connection, right? Okay. So let's solve the questions. What else? So the line current will be IA, IB, and IC. The neutral currents here, as you can see, there is no neutral here in delta connection. In Y connection, there was a neutral buoyant. Here, there is no neutral buoyant, so we will need to bring this one because there is no neutral current here. Finally, the active, reactive, apparent power absorbed by the load. As we did with the Y, we're going to do it here with the delta. So, let me start the solution. The load voltage is first. What is given here? EAB, which is line-to-line voltages, is given, right? No, but it is delta. So typically 1 and 2 will be the same. 1 and 2, the load voltage and the line voltages are the same here in delta connections. So let's calculate them in one time. So what does that mean? VAB is equal to EAB, VBC, right? Is equal. I'm not using E here actually because everything is in the load side. So let's just take what we put here. VAB, VBC is just only small capital letters, and VCA is VCA, and they are the same. What is given for us here? VAB is 220 angle of 0 volts, right? So let me call this one VAB. VAB, right? Between A and B, between line A and B, the voltage is 220 angle of 0, right? So now the other voltages will be the same, 220, 220. The only difference is that now phase shift based on this sequence. We are using ABC sequence, A first, B is lagging behind by 120, C is leading ahead by 120. So this is 220 angle of this angle minus 120. And this angle here for C plus 120. 1 and 2 is done. So this is the load and line voltages. They are the same. They are equal in delta connection. Right. Number 3, the load currents, the current that goes inside the load, right? So this is number 3, the load current. So let me start by IAB, which is this current. The current that goes inside this load is, by Ohm's law, is the voltage here over Z phase, right? So what is my voltage? My voltage is VAB over Z phase. What is VAB? VAB, we calculated from here. It's given actually in the question. This is 220 angle of 0 what is Z phase? This phase, this is some rectangular, so if you convert it to polar, 4 square plus 3 square, this is 5. This is in the first quadrant, and we have imaginary 3, this is 4. This is gonna be time inverse of 3 over 4 is 36.87 ohm. So this is over 5, 36.87. Right? 220 over 5 is 44. So this is 44 angle of 0 minus 36, or you shift this one up, minus 36.87 ampere. That's the load current here. Okay? Once we know IAB, we can bring the load current here, because they have the same value of RMS, phase shift of plus minus 120. So IBC will be 44, this angle, but now minus 120 degree. ICA will be 44, this angle, minus 36.87, but now plus 120 phase shift, ampere, right? Okay, good. So this is number 3, the load current. We bring the load current. Number 4, the line currents. So let me take this one out. The line currents, that's number 4. The line currents, we're going to use the formula here. The line current, which is IA, IB, and IC. Let me bring IA first. IA, according to the formula here, is root over 3 times the load current IAB, or the phase current, this one, and there is a phase shift of minus 30. So this is root over 3. What was IAB? This is IAB. We just get it here. 44 angle of minus 36.7, and there is an angle phase shift here by minus 30. So you have to put minus 30 with it, right? Okay. This will be root over 3, 1.7, 3 times 44. So this should give you by calculator 76.2, and the angle is minus 36 minus 30. Minus 36 minus 30 will be almost minus 60. Okay, so let's continue. This is IA, we bring IA. Now, once we know IA, the line current in A, then IB and IC will have the same value of RMS, 76.2, and a phase shift of plus minus 120. So this will be minus 66.8 minus 120 for B. According to this, so it's lagging by 120, ABC sequence. IC is minus 66.8 plus 120 ampere, right? So these are the line currents, and always line currents values are greater than load current values in delta connection. In Y connection, they are the same. Load current and line current in Y connected load are the same. Here they are different. The voltage is the same here in delta connection. Right. Last one is active, reactive, and apparent power. So this is our load. Our load is a resistive element with inductive elements. Resistive element will consume active power, watt, and inductive element will store reactive power, Q, L, because it's 6 L. So as we did with the previous example with Y connected load, we're going to do the same here. B is I square times R, not any I, it has to be the current in the load. So this is IAB, okay? And again, this is only RMS value. We don't consider the angle here. And I'm multiplying by 3 because it's a 3 phase, so the total is a 3 resistance, a 3 phase. So this is 3 times 44 square. Load current is 44 times how much is my resistance? My resistance is 4. So this will be something like 12 times 44 times 44. We're talking about 24,000 almost, or 23. So if you check by calculation, you should get something similar to 23 kilowatt. Or we can use also the other formula, which we used in the last example, 3 times voltage times current cosine of theta, right? But this one is direct. Q 3-phase is 3 times I square. Again, it's the load current times XL. So this is gonna be 3 times 44 square and times 3. You should get something here like 3 times 3 is 9, 44 times 44 is, 44 times 44, we're talking about 17.223, let's say, kilo var, right? And then finally you can bring S by taking the square root of B and the Q. So this is 23 square plus 17.3 square. We're talking about something like 3-phase, and we're talking about something like, by calculator you can do it easily, 29 almost kilovolt ampere, right? Okay, what about power factor? Power factor is here, so you can say cosine of theta z per phase, or typically B over S. B over S is 0.8, and it is lagging because it's an inductive with the resistive part. So by solving this example, we reach the end of lecture number 6, which covered basic of a 3-phase AC circuits. Mainly we are interested in the load side connection, Y connected load, and delta connected load. Okay, so if you have any questions or any comments, just post it in the blackboard and we'll respond to it, inshallah. Thank you very much. Good luck. We'll see you next week with lecture number 7. Assalamu alaikum.